Section 6.1, page 532, we're going to talk about power series. What is a power series? It just means that x is raised to some power in your series. It's identical to infinite series. The only difference is now we have an x in it. The power series is, if you expand it, it looks very much like infinite series that we just had, and also they work about the same way. Okay, we are going to be proving whether the power series converge or diverge and so on. And you think, however, the power series has have various interesting functions and characteristics and uses for it that makes the infinite series much more useful. Now, so to look at the power series, we have, generally speaking, the power series, the regular one, which is x to the power n, or you can base it at a different point. That is, you can have x minus a to the power n. That just means your series is based at a instead of x. But most of the time, when a is 0, of course, the power series reduces to that one, and that's where we mostly focus on. The one thing worth mentioning is in power series, the number 0 raised to the power 0, yeah, like this, which is normally not defined, okay? In power series, we define it as 1 for convenience. Otherwise, the power series will have a undefined point, which is pointless, okay? So defining the power series when it's 0, then we'll simply call it 1. And then everything works out nicely. Now, so let's go to the next page where we need to prove the convergence of the power series. That's the only thing we really care about, basically, about power series, is if it converge. If it diverge, it took off. And what are we supposed to do with it? Nothing. There's nothing we can. It's useless if it diverges. But so we care about when does this thing converge. And to prove power series converge or diverge, we'll be using the good old ratio test and the root test and all those other tests that we learned in the previous section. But first, let's look at when does the power series converge, and that's theorem 6.1 on the next page. There are three properties. Okay, let's say you have a power series. The book starts out with a power series that's based on some point A, and for convenience sake, we'll just pretend that A is 0. Now you notice that if A is not 0, then you can simply assume that the power series is something you let, look at the bottom here, okay, where you let y equals to A down here, right? And you translate it into a different power series, which that is 0, and the two series will have the same properties. That's why we can, for convenience sake, only consider the power series that's based at 0, but the other one works the same way. You just moved it a little bit, okay? So what are the properties of the power series? The power series satisfies exactly one of 3 conditions. Okay, very important. So it has to be one of the 3. Any power series, this is true. Number 1, the series converges at x equal to a, or in our case, x equal to 0. It always converges at 0 because if x is 0, then everything gets knocked out, right? Except the first term where n equal to 0, where it becomes C0 is the power series, because everything else is, because you have an x there and everything else becomes 0. So that's why 0 to the power 0 has to be defined as 1 for power series. Otherwise, it doesn't make any sense. So so that's that. So the first condition is fine, okay? Either that is true, the series converges, that is, a power series at least converge at x equal to a or at the point 0, but that's not really very exciting because all the x's become 0. The question is, does it converge anywhere else, right? Okay. The next question is the series converge for all real numbers. That is, the series converge everywhere, and that is possible. And if that's the case, that's good. That's great, in fact, if the series converges everywhere, if we can prove it. And that's also good. But here's the third condition. That's the most critical one that we're going to be focusing on, is that the series doesn't just converge at 0 and doesn't converge everywhere either. It's not all or nothing. It converges at sometimes, but not other times. Okay, and the third condition is that there exists a number such that the series converges if x is less than r, and then diverges if x is bigger than r, the absolute value of x. In other words, on the real number, the series, oops, why do I have a vertical line here? Well, that looks terrible. Yeah, I will wipe that off. Here we go. All right, so the series converges at, so here's your real number, all right? And we're focusing at 0 right now. So our series has a focal, what is this called? Well, whatever it's called. The point is, there is a range, okay, from minus, that's r here. There's a range such that it converges in this range and then diverges outside the range, both sides. So this is the convergent area, okay? This is the converge area. And everything else diverges, and backwards here also diverges. This is the only convergent area. That's the third situation. So any power series will fit one of these three situations. Converge only at 0, converge everywhere, or converge has a defined area that has a radius of r, and then diverge everything else. Now so to prove this theorem that a power series it has to be one of those three situations, and we are going to prove it by this sentence right here, which says that now right here in the book, okay, down here, where it says that if there exists a real number such that this thing converges, a real number meaning that d is bigger than 0. Okay, if it's 0, it's just situation 1. That's not exciting. Now, if there's a number that isn't 0 such that this converges, where if you plug the d into x, okay, then the series converges. Then it converges for everything that's less than the absolute value of x. So in other words, if it converges at some point, it converges everything that's less than it. And that's the main thing we need to prove here, okay? The most important point. That is, if a series converge, then it converges for all of x such that x is less than the d that we found that to be convergent. Okay, now to prove that, we have to, we'll write stuff down, okay? So here's the assumption. Well, let me write down what we're proving, such that, okay, we are proving that here's what's given, okay? Assuming that c and d to the power n, d to the power n converges from 0 to infinity for some d bigger than 0. Yeah. Actually, I think, yeah. Well, absolute d bigger than 0. Well, of course, it's all right. So then this is the condition, okay? And then converge. This thing converge, C-O-N. So then what we're trying to prove that is this thing converges for all, so then it converges, okay, then is the series converges for all. The series converges for all of anything x that's less than d. It's important to write down what we're proving, okay? Because otherwise you're going along, forget what you're doing. So it's important to write it down in such a way that it's clear to yourself. So that's how I would write it. You might write it differently. So whatever it takes to write down in a shorthand that this is what we know, this converges for some number d, and here is what we're trying to prove, that it converges for anything that x, when you plug in the x here, that's less than d. All right. Now, so then the next step we're going to do is that because this series converges, right, that means this sequence, the Cn dn, Cn times dn, that is what these terms in here has to go to 0 as n goes to infinity. That is what, the divergence test or something. Each term better go to 0, okay? Otherwise you're going to have a divergence situation. And so that's the first step. Because of that, then there exists, okay, backwards e means there exists some large integer n such that this number is going to be less than 1. So where the absolute value of this thing is less than 1, I mean, it's going to 0. So sooner or later, they are all going to be less than 1 as long as you pick an n that's big enough. But the n is fixed. It's big but fixed. Okay, so we pick the number, a fixed number where all the little n's that's bigger than big N is going to make this situation less than 1. All right. And that means, and then we're gonna play some tricks in order to prove stuff. The trick is that we're gonna write this down. Okay, the Cn x to the power n is we're gonna write it like this. Okay, write it as Cn dn, plug d in there, and then times xn over dn. Okay, that is true because we have added the d in the numerator and the denominator, so it cancels out because of that. And why are we doing that? Because this is a trick, okay? And that is going to be less. And what about it? Now, being that we have stated that this thing is less than 1, okay, don't forget this part, right? So this thing right here, okay, is less than 1. We just said so, okay? And then therefore, it's less than or equal to 1, I guess. Okay, we'll add the equal sign, doesn't hurt anything. So this is less than or equal to 1, which means that, look at the next page, this thing is, so this thing is then, the next inequality would be Cnxn is less than or equal to this thing right here, xn over dn. Okay, that's the next step. Now, and then we are going to have, so then now we're going to look at the series themselves. So then the series, the original series, this is our series xn, okay, is going to be less than or equal to the series of this thing. Now, what is this? This is dn. We are going to draw it like this, okay? And that's the same thing as here. And if this number right here is less than 1, then this becomes a geometric series, right? If this is less than 1, then that whole thing will become a geometric series, which looks like the geometric series is something like this, right? Rn, sorry. Now, if it's going to be a geometric series, the rules of the geometric series says that if r is less than 1, if r is strictly less than 1, then the geometric series converges. And therefore, and we have come to the end of the proof. Therefore, by the being that this converges for if x over d less than 1, we conclude that this also converges if x over d less than 1. And that's the comparison test. Okay, so given that, then so this term converges. Where's the summation starting? In here, the summation is starting at the big N to infinity. That's what we are, because we chose big N. But if, well, as long as the tail end of the series converges, then the entire series from 0 to infinity also converge. Okay, because the convergence depends on the tail end of a series alone. We don't care what the first n terms do because they're finite. So they will converge or diverge based on the tail end. So this thing then converges. Okay, then we have proof that this thing converge. And that's what we had set out to prove. We were trying to set out that this sum is converged if x is less than d. Is it less than, equal to, or just less than? Let's see. Yeah, originally we just want x less than d. Anyway, so then because of this here, right here, so convergent if x over d less than 1, or if x is less than d in absolute value, right? Yeah, convergence if x is less than d. That concludes the proof of this part that we are trying to prove. Now at this point, however, once we have proved that, what we have proven is that as long as there's a number that's not 0, that where this thing converges, then everything less than it converges, like this, okay? We have, here's a 0, okay? That's the center of our our series. And we found some d where that's bigger than 0, where this thing converges. Then anything less than that on both sides, that's minus d here, on both sides, it will converge in here. Now, what that means, that is enough, this is enough information to prove our theorem. And why? Because given a power series, it either converges just only at A, which is fine, or converges everywhere. But if it doesn't do either, that means it must converge at some point B that's not 0, right? And if it converges at D, then it converges everything inside D. Okay, so which means that if D is an infinity, it doesn't converge everywhere. That means there's a bunch of D's, right? D1, D2, etc., where this thing converges. Then if D doesn't go to infinity, then you have something called the least upper bound, from which here's the D, that's the smallest number such that everything on this side converges and everything on the other side diverges. That's because if there's anything out here, okay, if nothing in here can converge, right? Because everything inside D has to nothing in here diverges. So if there's any point that diverges here, then everything beyond it has to diverge also. That's the contrapositive. Because let's say there's another D here, say D2, which it diverges, then everything out here cannot converge, because if something here converges, everything inside converges. Remember that, right? Within the absolute. So once you have a divergent point, everything past it has to diverge. So you can find something called the least upper bound, okay, where it divides everything into two parts, convergent, divergent. And that concludes the proof, is that any power series has to follow these three conditions. Converges only at 0, converges everywhere, or it has a radius of convergence. Okay, this least upper bound is called R, the radius of convergence, where it divides things on both sides. Convergent on the side of 0, divergent everywhere else. Now, to calculate radius, what the power series radius of convergence requires something called the ratio test, the root test, all those tests we learned before. And so we're going to be doing some of that, quite a bit of the stuff from the previous chapter in order to find the radius of convergence. But other than that, however, we're not doing anything new besides realizing that in the case of the power series, which is a special case of the infinite series and is very useful, which is why we're learning specifically this thing, it has often has a radius of convergence. Of course, the radius might be 0 or it might be infinity. But most of the time, however, the radius is some point that we're interested in. Okay, there's a point where it diverges past it and then converge as long as it's on the inside. All right, so now that we have proved theorem 6.1, let's look at the next thing. Okay, so the next page, of course, we see the definition of the radius of convergence. As I have mentioned, is that everything converge. I should mention that exactly at this number, there's no telling. It might converge, it might diverge, depending on the series, as you can remember in ratio and root test. When rho equal to 1 in the ratio or the root test, it can go either way. It depends on the specific situation of your specific power series. Okay, now, so knowing this, let's look at example 6.1, which is you're trying to find the radius of convergence. Where does the series converge? Where does the series diverge? To do that, we're going to do exactly what we did in the last chapter. There's nothing new here in applying theorem 6.1. So please do example 6.1 as part of your homework. All right. Next, we're on page 537, where we are trying to represent functions as power series. Now that is something that you have done twice in two different previous sections already. Okay, what you do is that you write the function in the form of 1 over x. And because did I say power series? I mean the geometric series. That because the geometric series is also represented by an infinite series, right? I mean, here's the geometric series, which looks like that. We are fairly familiar with it by now. You know that it also equals to this, because the geometric series has a solution. Okay, it's just 1 over 1 minus x. But the solution is limited. It's only true for x less than 1. And therefore, there are various other functions that we can hit it and make it, force it into the geometric series, and therefore write an infinite series out of it. And we've done that several times. So, and that's example 6.2. And then again, example 6.3. Now, in example 6.2 on page 538, there's a graph of how you may simulate the function with a partial sum. That is, let's see if, say that is, okay, let me wait for the camera to focus. It's focused. Okay, see, the top function is 1 over 1 minus x. That's the original function, right? And if you do the partial sum, S2, you only got 2 of them, it looks like that at the bottom. It gets the approximation gets, it's pretty good when it's small, right? Between 0.5 and minus 0.5. Whereas as you get closer to 1, then the approximation gets worse. So as you can see, S2 is not as good as S4, and which is the 4 partial sum. And then S6, you add more terms, you get a little more accurate. But generally speaking, the accuracy falls off as you get close to 1. And then in the homework, then there will be ways of plotting the power series, the partial sums, as compared to the original function. Or maybe there isn't any original function, but either way, you will plot the power series of the approximation. So that can be done in the Desmos calculator. I have the link down there. And remember to type in the summation symbol for the power series. You just type in the letters SUM for sum, and then the summation series will pop up. So please do homework example 6.3 and 6.4, which are nothing that you haven't done before. Okay, that is you just force some other function into the geometric series format, and then sum it up and turn it into an infinite series. Of course, it only converges in a short range between 1 and minus 1, or in your different function that might be adjusted due to it being depending on the function itself. So so please do example 6.2 and 6.3 as part of your homework. So we have come to the end of this section. For homework on page 541, please do problems 7, 11, 15, 19, 25, 31, 33, 37, 41, 45, 57, 59, and 61. Most of these problems are sort of repeats of the previous chapter, but there are some new ideas that we can explore that makes it quite interesting. So please go do your homework, and when you come back, I want to talk about some of it. All right, now that you're done with the homework, let's talk about it somewhat. Now, the homework in this section is almost identical to stuff we've done in the past, except easier because now you have an x in your series, which after you apply the ratio test, things tends to come out very nicely and neatly. For example, let's look at problem number 15, Okay, you apply the ratio test and then let n goes to infinity, and very soon you can calculate that the radius of divergence is the radius is 2, where you diverge from -2 to 2. Now anything on the endpoint will diverge. Now, problem 19, a similar situation. You apply the ratio test, okay, and you calculate the radius of divergence, and then you even figure out what's happening at the endpoint. In this case, the endpoint does, both endpoints converge from minus pi to pi. So therefore, the range is from minus, the brackets means endpoint included, okay, whereas here the parentheses means endpoints excluded. Next, number 25, what are we doing? Yeah, the same kind of thing. You apply the ratio test, cancel out a whole bunch of stuff, and end up with the radius convergence. And next, problem 33, the same thing. Oh no, the problem 33, we're doing something different. We are trying to beat the function into the geometric series format, okay? So you do that, and then you come up with some infinite series and figure out what the radius of convergence is, same as the problem 37. Next, we have problem number 41. Again, a geometric series. We're going to beat it into the, a function that we're going to beat it into the geometric series by first we'll take out the x squared and nothing, I guess. X squared and the 4, yeah, we'll just take out the x squared. And the rest of it, we'll plug it all into the formula and clean it up a little bit and come up with something, like such as the radius of convergence. And 45 is the only problem that's slightly different, not that different. Instead of a ratio test, which we've been using this whole time, we're going to do the root test. But the result is the same, okay? We're going to come up that the radius of convergence is 2, and that's about it. Now you might think it seems like we're not getting very far with the power series, as everything seems easier than previously. Well, that's because it's just the first section, okay? The power series will get more difficult as time goes on. But for the first section, we're easing you into it gently, so you're just doing some identical stuff that you did in the previous chapter, plus they're mostly easier than what we did before, which is a nice relaxation time before the storm hits. Now, so for the next few problems, we will do the graphing with the graphing calculator. Okay, now for next we look at 57, which is to graph some geometric series, the power series for the geometric series. Well, whatever. The point is, the Desmos calculator actually has this as an example, okay, which I put a link in under the video. You can use that one, or you can just type it in yourself. But for this problem, I will use the one that Desmos provided, because they typed in the exact same problem. And whereas for the others, I will just type it in myself. Now the Desmos calculator, as I have plotted here, see? In fact, as they have plotted, I just changed something like, I put n equal to 10 in this case. As you can see, even when n is only 10, the simulation is very good. And the reason you know simulation is very good is that the green line is the original function, 1 over 1 minus x. The red line is the power series simulation. And look at how close they are when it's, say, between negative 0.5 to positive 0.5. You can't even see the difference. And the n only went up to 10. So you notice that it's an excellent simulation of the function. You might also wonder, why are we simulating it again, doing this? And because sometimes, well, we know what the geometric series converge to, but there are a lot of things that we don't know. Other functions that we don't know how it converge. So we use something we do know to see how good the power series works. So that way it gives us an idea of how good it works on functions that we don't know what the final equation is. And so that is problem 5.7. And then the next one is similar. Where the next one, I simply used the regular Desmos calculator and typed in the series. Okay. All right. The series is xn over n squared, right? And as you can see, I have 3 of them typed in, and then it's around the series centered at 0. So as you notice, and whether it is the 10th or the 50th or the 100th, when n goes to 100, the series is very, very close, around between minus 0.5, no, minus 1 to 1. Although I think the series, the convergence, yeah. Anyway, so as you can see, the series works very nicely. Even when n is only 10, okay? N going to up to 100 didn't really gain a whole lot. Okay, so that's problem 59. And next, let's look at problem 61. Where is it? Okay, now 61. Okay, here's the graph for 61. 61 is more interesting because we're simulating the sine function. The sine function happens to, we'll figure this out later, okay? How to calculate the power series of the sine function. But for now, we are just given the power series and take a look at it to see how good it is. Now, take a look at my plotting of this. Now notice in this graph, I have the original one is the color on the bottom. What is that, blue or something? Yes, so that's the original sine series. And then the red one is the approximation only with 3 terms. As you can see, the red approximates, even though it's only only have 3 terms, it approximates it really nicely up to like +2 and -2, right? Maybe a little more, 2.5, before it finally falls off. So the sine series approximation works extremely well. And yeah, and by 5 terms, you can't really tell the difference, right? I mean, at least from pi to minus pi, which is where I'm plotting here. Now, so the 10th terms, I turned it off. So it's not being plotted here so that it doesn't get confusing. But as you can see, the 5th term, you can't even tell the difference between the blue and the purple. That's because, well, you can't see it, okay? Because it's right on top of each other. It's an excellent approximation. So that is how the power series simulate the sine of x. And with that, it marks the end of this section. Oh, I should mention that when you type stuff into the decimals calculator, do not retype anything. Okay, just you just type the first one and then copy and paste it into the second one. And don't wear yourself out typing all this stuff forever. And yeah, that's about it.